Hello everyone, this is Tanzim. Welcome to my class presentation for ECE 591. Today I will present SAIL, Analyzing Structural Artifacts of Logic Locking Using Machine Learning. This paper was published in IEEE Transactions on Circuits and Systems. Let's start. Look at the supply chain here. Certain amount of challenges. With the ever increasing design complexity and integrated circuit manufacturing cost, outsourcing fabrication offers best financial benefits for design companies. Unfortunately, sophisticated hardware based attacks are emerging on the globalized supply chain, causing various concerns such as intellectual property theft. In particular, most chip designers rely on potentially untrusted third party fabrication facilities. Such a trend diminishes a chip designer's control on the IPs and makes them vulnerable to various forms of attacks, including piracy, reverse engineering, overproduction, and malicious modifications. To address these security issues, hardware or logic locking techniques have been actively studied for the past decade. So, what is logic locking? Logic locking is a technique into a circuit design such that it produces faulty outputs whenever an incorrect key is triggered. Let's look at the example here. It inserts some key gates into the original design and makes the design locked. This design will work if correct key bit is triggered. There are two types of logic locking, functional and structural. In functional logic locking, key gate is inserted on a device. As for example, if I add a key gate in error, it will be functionally locked and it will work if correct key bit is inserted there. But functional logic locking keeps some track on key gates detection that opens the door for key bits extraction. We need to lock the design in such a way that attacker cannot be able to know about what the key gate is. And that is why structural logic locking is needed. In structural logic locking, the technique is applied on the design content itself because an attacker can get the netlist by reverse engineering. So, in structural logic locking, key gates are inserted inside the design and local transformations are made. Local transformation is very important. Otherwise, it will be thrice easy to guess the key bits by visiting the key gate. In this example, I have added a XNOR gate into a design as it is a XNOR gate, so the correct key bit is 1. After the local transformation, it seems like that I have inserted a XOR gate and that will make the attacker confused about the key guessing. In a simple term, we can call this local transformation as synthesis. Synthesis is basically logic simplification. It simplifies locally by modifications, but the output will remain same. In particular, synthesis can be done using a software named ABC. Let's look at the simple example of synthesis. Here, XOR gate is inserted into an original design to make a structural change. By seeing this, we can easily dictate that the key bit is 0. But after synthesis, it will not be easy to guess the key. Seemingly, it can be in mind that inverter is pushed up as a key gate. Still, there are some problems on the structural changes, and that is local and predictable. So in next we will see some observations. Basically, synthesis is made to camouflage the key gates. Certain scenarios can be happened here. Number 1, there might be no changes on key gates or the surrounding gates. We mark it as level 1. There might be changes on the surrounding gates, but key gates remain intact. Level 2 is marked for this scenario. And in level 3, key gates can mix with the surrounding gates and transform a new structure. This level is complex to guess, and this is the level we want always. Here I will show a navigator for a complexity level. Look at this table. This analysis is taken over 7 largest ISCAS 85 benchmarks and with arithmetic logic unit designs. For, for 57,000 gate localities, we note that 16% of key inserted localities do not go through any structural changes. Moreover, 79% of localities only show level 2 changes that are very easy to revert using certain rules which can be manually learned through statistical methods. Only 5% of the localities are properly obfuscated. However, most of these designs are predictable and can be locally reverted as well with the help of statistically generated rules. In the previous section, we have established that the changes induced by logic locking gates are local and limited. Let's go one step further. Given the designs before and after synthesis, if we measure each transformation, we will observe that very few rules are used by the synthesis tool for carrying out most of the transformations. Here we can see that 30% of transformations are done by 50 rules, and lastly only 1000 rules govern the 81% of changes. By learning this limited number of rules statistically, it will be easy to revert the changes, and most important thing, this deterministic behavior is the main reason why a machine learning reversion attack is possible. So, after observing all the steps, what does basically Sail do? Sail basically takes a synthesized locked design and reverts it back to pre-synthesis design. It is a ML guided attack. So, what is the benefit then by Sail? Look at the example. Synthesized netlist design is shown here with original netlist. Sail takes these as inputs and gives back a pre-synthesis form netlist. Basically, we can tell this as recovered graph from a synthesized locked graph. This pre-synthesis form actually paves the way for an attacker to carry out key guessing and also others reverse engineering attacks. Dataset. As discussed before about the predictable nature of logic locking, Sale learns from this behavior. It is prominent that Sale will take input of a post-synthesis subgraph and predict the corresponding pre-synthesis recovered subgraph. So, both input and output is graph and Sale is trained on pre-synthesis post-synthesis subgraph pair. But how this pair will be made? Let's look here. Hardware design is basically connected of gates and we can consider those gates as graphs. Gate type itself can be taken as nodes and connected wires can be edges. We will extract the feature for each nodes on pre-synthesis and post-synthesis subgraphs. For feature extraction, we will consider the surroundings of key gates. For each key gate, localities will be taken by BFS, that is breadth first search, and their connectivity will be taken by adjacency matrix. For representing the key types, we will make a vector representation by hot encoding. The localities will determine get how the surrounding gets I want, and hot coding represent total number of unique gates in a particular design. At the very next level, the subgraphs will be flattened to make a one-dimensional vector representation. For locality of 3 gates and 10 unique gate types, the vector size will be 1 by 39. 39 will be comprised by 30 plus 9. 30 is from 3 gate types, 3 into 10, and adjacency matrix size was 3 into 3, that is 9, in total 39. Now this input will be fed into 128 dense layer and each of them propagated into n plus 1 channels for predicting a locality of size n. The first n channels are for the n gate predictions and last channel is for predicting the adjacency matrix of the locality subgraph. Mentioning again, G is the total number of gates in the standard cell library being used. The accuracy of cell is taken for different sorts of logic locking techniques. Here, RN XOR means XOR based random logic locking. RN marks for marks based random logic locking, and so on for others. Key point is every logic locking technique is vulnerable to sale and it can recover almost 80% of them into pre-synthesis state. The sequel logic locking and cyclic logic locking does not show anything for FIR designs because the locking algorithm fails to terminate for FIR designs. Now I will discuss another machine learning guided attack, that is OMLA, Oracle-less machine learning based attack on logic locking. Like SAIL, OMLA takes a locked netlist but it does not predict any recovered subgraph. Moreover, it predicts key bits directly by analyzing the characteristics of subgraph. One key point for OMLA is node features and levels because it uses input and output information and it considers the whole netlist as undirected graph. Another is, unlike SAIL, as it is considered as a graph representation, so graph neural network is used as a model. But like SAIL, no pre-synthesis subgraph is needed for the OMLA. The dataset generation for OMLA is pretty similar like SAIL. It just consider the subgraph as undirected and extracts the feature by hope technique. Hope 1 dictates the gate surrounding directly and hope 2 goes one step back for mutual connection and so on. There is no pre-synthesis post-synthesis pair here. The nodes are labeled by input-output information to maintain direct connection for the adjacency matrix. There is not more information about the graph neural network architecture in this paper. It only shows the batch sizes and basically it seems very ambiguous to me. So I did not mention the architecture here. OMLA outperforms SAIL and Snapshot, which is another machine learning guided attack, and for some benchmarks, OMLA is able to rise above 97% accuracy. That's all my presentation. Thank you for your patience.